Hello everyone, I'm Varshini from Sri Venkateshwara College of Engineering, pursuing my computer science engineering in data science. Today we are here to discuss the subject mathematics and my topic is cyclic groups. So what is a group? Definition: a group is a set G with a binary operation that satisfies closure, associativity, identity and inverse properties. It also includes the commutative property. If any function or a binary operation modulo that we consider is satisfying all these properties, then it will be considered as a group. And we have the notation, which is inside parenthesis we write G, which is the set, and the operation, that is dot in this case. And group provide the foundation for many mathematical structures, and they help us model symmetries, algebraic system, and understand the other concepts with the help of grouping concepts. Next, what are cyclic groups? So, a group G is cyclic if there is an element small g that belongs to G such that every element in G can be written as G to the power n as an integral power under multiplication or under addition. And the small letter g is capable of generating all the elements of capital G in itself. So we have the notation which is in the arrows bracket here, and where G is called the generator because the small g is the element which is able to generate all the other values of the cyclic group. And cyclic groups are generated by a single element, making them among the simplest and most well understood types of groups. They serve as an excellent model for learning abstract algebra concepts because of their structure and predictability. Examples of cyclic groups: integers under addition, that is z, which is the set we are using, that is integers, and plus is the addition symbol or the binary operation that we are considering, and is infinite and cyclic, generated by 1 or minus 1. Modular arithmetic is Zn, that is cyclic for all the values of n. And we have multiplicative groups, that is Z7 into multiplication star is a cyclic group generated by 3. Here 3 and in the first case 1 or minus 1 are the small letter g and they are called the generator. And cyclic groups occur naturally in many number of systems and applications. These examples illustrate both finite and infinite cyclic groups and show how modular arithmetic relates to the group theory. What are generators in cyclic groups? As I've told earlier, a generator G produces all the elements of the group by repeated application of the group operation. Let's say we are considering the capital G and multiplication. But for that set G, small letter g will belong to the capital G, which is the set, and the element will belong to the set. And this element in individual is capable of using the operation that we are giving and generate all the other elements of capital G. All the other elements without repetition, then it is called a generator. And multiple generators are finite cyclic groups that have multiple generators depending on the group's order. And in a group of order n, any element whose order is n is a generator. For example, in Z7 plus that we discussed earlier, any non-zero elements act as a generator, creating the whole group through repeated addition. Any number you consider and try to repeat the same addition operation in this set, it will give you the other elements, remaining elements of the same set. Subgroups of cyclic groups. What is a subgroup? Every subgroup of a cyclic group of order n is cyclic and has the order d. And for divisor d of n, number of subgroups is equal to the number of positive divisors of n, and this means that a cyclic group of order 12, for example, has subgroups order 1, 2, 3, 4, 6 and 12. Each subgroup is generated by element whose order is a divisor. So what this basically means and what we learn from this is, if we have like one group that is G, which is a primary set that we are using, and there are subgroups of G as J, K, H, then J, K and H are also cyclic, considered as cyclic groups if G in the beginning was a cyclic group. Next, we have the properties of a cyclic group, and all cyclic groups are abelian, meaning the property operation is commutative. When do we consider a function or a cyclic group to be abelian? That is when it satisfied all the 5 properties that we discussed earlier. That is, if the function is closure property, falls under closure property, associative property, commutative property, inverse property and implicit property. Every subgroup of a cyclic group is also cyclic. As we discussed earlier, if the subgroup is cyclic, then the main group is also considered as cyclic. And the order of any element divides the order of the group. If we consider the order of a small element G to be 3, and that is able to divide the order of the whole group or the entire set that we have considered. These properties make cyclic groups highly structured and easy to analyze. The commutativity and predictability of subgroup structure are critical when they come to studying complex algebraic systems. Applications of cyclic groups. Where do we use cyclic groups in our day-to-day? It is used mainly in cryptography. It is used in algorithms like Diffie-Hellman key exchange that we have an example here in the image. And in number theory, it helps in understanding the modular arithmetic and primitive roots. And cyclic groups form the backbone of many modern cryptographic systems where finding generators and order is key. It is mainly used for debugging as well, or for debugging software applications where cyclic groups play a very important role, and they also appear in coding theory, signal processing, and symmetry analysis. All these topics are very crucial for developing any type of software or also in general to solve mathematical problems. Here's a recap and conclusion of everything we studied till now. Cyclic groups are simple yet powerful structures in group theory. They are easy to understand, classify, and appeal to real world contexts that make it very easier for us to resonate with these topics. So that will be the end of this explanation. Thank you.